Hey everybody, welcome back. Today we're going to be talking about the queue data structure. This is a first in, first out structure. You can think of it sort of like a line at a bank. If you're the first customer in line, you're the first person to be served and out of the bank. We're going to implement it in Python, and it's got two fundamental operations, Enqueue and DQ. Enqueue is like push. If you watched the last video, it's kind of like pushing onto a stack, and DQ is like pop. Can't wait to get started, so let's get going. Alright, so we're going to implement the queue using a singly linked list, but we're going to modify it a little. Recall that in a previous video I did the singly linked list using a pointer to the head node, and that's all we had. In this case, what I'm going to do is point to both the head and the tail, but I'm going to call it the front and the back, because we're talking about a queue, and front and back sort of makes more sense. So with that out of the way, let's consider the initial queue, which is empty. Both front and back point to null, and then what's going to happen is, let's say you want to enqueue something. In other words, add something to the queue, like the letter A here. So we have this letter A, and we want to insert A into the queue. Well, the first thing you're going to do is create node A out of that letter. All you have to do is set front equal to node A, and you're done. Your queue now has a pointer to null, which, by the way, is where back is pointing to still. So then, let's say we want to keep enqueuing. You enqueue the letter B. Now that you already have a node, what you're going to do is you're still going to create a node B, and then you're going to set the fronts next to node B, and its next is still null. But then you end up having to set B, this node you just added, that becomes the back. And then you end up with this queue here. So now you have a front and a back, and it's all pointing to null. Keep in mind, all nulls are the same. That might sound kind of trivial or ridiculous to say, but if you look back at this graphic, you have two nulls. In reality, it's all just null. So when you go to set back equal to B, you know, you're still pointing to null there. It's the same null as you had before. And so you end up with the queue you have. Now let's say you enqueue C. In that case, you already have a front and a back, and then you just create a node at a C. You set the current back equal, its next equal to the new node, and you set back equal to the new node because now you have a new end of the queue, and you're done. And you have A, B, C in the queue. Now let's say you want to dequeue or remove a node. Well, you're always going to remove at the front, and it is a singly linked list, so this is a good design choice. The front is easily accessible in a singly linked list. So is the end, but we're adding, when you dequeue, it's first in, first out. So you're always going to remove at the front because that's the leftmost item is the one that you first added, and the one at the end is the one you last added. So you can set remove node, a variable equal to the front, whatever front is pointing at, and then you set the front equal to front's next, because that will become the new front once you dequeue. Then you set remove nodes next equal to null, and you're done. Because at that point, you have a new queue, as shown here, with the original front removed. So now I have a challenge here. See if you can write the algorithms for enqueue, for dequeue, and dequeue here should return the string value, as you can see. Get the front. In other words, show me what's at the front of the queue without removing it. It's kind of like top in a stack. If you watched the last video, top only showed you what's on top, and pop actually took it off the stack. Same concept here. Get the length of the queue, find out if the queue is empty, and that's a Boolean, returns true or false, and then print the queue. So go ahead and give it a shot before you move on with the video. Try and create algorithms for these. No problem if you're having struggles with it, because I'll go over it next. Well, I hope you had some luck creating those algorithms, but don't worry if you didn't, because we're going to go over them right now. And to save time, I've listed the functions we want to write algorithms for already here, and so we'll just go down the line and do them one by one. So first of all, enqueue. As I showed in the graphic, when you want to queue a new item or you want to place a new item into the queue, the first thing you want to do is have a new node created. And so I'm going to assign to new node the node with the new data. So if you have a queue of letters or string characters, then you create a node out of that and then assign it to new node, suppose. Then if the queue is empty, remember you always have to care for the situations where you have, the edge cases where a queue might be empty, or if a stack was full and you try to push onto it, those types of things you have to be concerned about. So if it's empty, then you just set the front equal to new node. Else if the front's next is null, then what you want to do is set the next equal to new node. Set front dot next equal to new node, and then set back equal to new node. And this way, if it's not empty, in other words, you have a single item in the queue, then this is what you're going to do. Otherwise, you have a front and a back already, and so you don't have to move. You have to move the back, but you move it forward to the next node that you just added. So back, in that case, back.next, back will be new node. And remember, we're going to, just thinking forward, we're going to want to know what the length of the queue is later. So why not just do that, update the length of the queue anytime you add or subtract something to the queue. We'll make the queue length initially be 0, and every time you add something to the queue, we want some size variable to be incremented. So we'll set size equal to size plus 1. All right, hope that makes sense. Let's take a look at dequeue. And now I want to make sure that it's not empty before you start dequeuing. So if QUE, I think I spelled that right. If queue is not empty, then you can do some actions. You set the remove node equal to the front, or assign front to remove node. Maybe we'll call it removed node. If the front, its next is null, then what are you going to do? In other words, you have one item in the queue. So then you just set front equal to null. And then else if front.next equals the back. So in other words, you have two items in the queue. Front will become the new back, and you set back equal to null. Else, what are you going to do? You're going to set front equal to front.next. So what we do is set remove node equal to whatever's at the front in this case, and then if you have a whole bunch of items in this queue, in this else block, what you're doing is just set front equal to whatever was to the right of it, and that becomes the new front. And then what you want to do is set removed node, its next equal to null. You're unlinking it from the whole list by doing that. You're going to set the size equal to size minus 1 now, because you just removed a node. And then you're going to return the removed node's value. So we could return the whole node and then get its value later, but I've decided in this design to just remove the node and return its value. So if the node contained the value letter A or B or something like that, just send that back when you dequeue. Get front is much simpler. So if the queue is not empty, then you'll just return front's value. Length is equally simple, because all you're going to do is return the size. And to check if it's empty, you're just going to return front is null. In fact, actually, I'm going to write it more in pseudocode. If front is null, return true. What we're going to do here, and I'm not going to worry about formatting, and because this is an algorithm, we're not going to worry about the details of the formatting here. I'm just going to say if queue is empty, then you're just going to print some sort of empty message. Else, you're going to set the current equal to the front, and then while current is not null, you're just going to print current.value and go to the next node. I think we've written algorithms for all of these functions. And so now we can go ahead and start implementing these in Python. All right, so I've opened up PyCharm, and I'm going to go into new project, and I'm going to call the project Queue, Queue, and click Create. And we have a new project called Queue. And so here, I'm going to right click on the queue and we're going to start creating files. The first thing I'm going to create is the node class because we're going to use that to create our singly linked list, which we're using to implement the queue. So I'm going to call this node. So I'm in my node class, and it's just like we've done before. In fact, we could have copied it and pasted it from previous node classes we built. And we're going to create an initializer. Every time you create a node, its value will be set to the value you provide, and I got to provide that as a parameter. And then we're going to take the next, and it's going to initially point to nothing. And I'm going to now start programming the list queue. Say new Python file, list queue, and now we're in list queue. And we're going to need to import the node. So from node, import node. And now class list queue. It's also going to have an initializer, and it won't take any parameters, but the front is going to be set to none. The back is going to be set to none, and the size is going to be set to 0. So next, what we want to do is, let's say we implement some of the easier functions first. For example, definition is empty, and all that's going to do is return, or if front is null, return true. But a quick way to do that is return not self.front. So what this will do is if front is null, in other words, if it doesn't exist, if not, then this thing will return true. Then length of the queue, that's going to return the size that we've stored. And this is why I've called this length, because if I call it size, that's the same name as the variable, and you can't do that. You're going to run into an error, which makes more sense anyway because you think of a queue, you think of its length. And now we're at define Enqueue, and that's going to take a parameter. We'll call it new data. And remember, we just need to create a new node, and it's going to be a node with the new data. If it's empty, if the queue is empty, then just set front equal to new node. Else if the front, self.front next is none, self.front.next is equal to new node, self.back is equal to new node, and then else self.back.next is equal to new node, and then we're just going to update the size. And we could just write plus equals 1. Now let's define dequeue, and we don't need to provide any parameters, as we discussed. If the queue isn't empty, then removed node will equal the front. If the front's next is empty, is null, another way of saying that is if not self.front.next. That's the same as saying if self.front.next is none, then self.front is equal to none. So in other words, if you only have one element, just set that front only element to none. Else if self.front.next is equal to self.back. So in other words, if the next element from the front is the last element, then self.front is equal to self.back, and then self.back is equal to none. Then else self.front is equal to self.front.next, and then what you're going to do is, in any case, reduce the size by 1 because you just removed something from the queue, and then removed node.next is equal to none, and then return removed node.value. And now let's figure out what we want to do here with getFront. So define getFront. You need to make sure it's not empty, and in that case just return the front value. Now let's go to printQ. So I'm going to format a little bit, put a little spacing in here. So I want to print a line, and then if self.isEmpty. So if the queue is empty, I just want to print the queue is empty. Otherwise, what I want to do is set current equal to the front, so we can iterate through the list and print as we go. And I'm just going to say print, first of all, front, so we know that we're looking at the front there at the beginning. And if we type end equals this empty string, that we know we're not printing a new line afterward. And then while current, in other words, while current is not none, if not current.next. So in other words, if current.next is null, then what you want is some variable I'm going to call arrow be this, an empty string. Otherwise, if it does have something next to the current value, then what you want is arrow to be this sort of arrow string here. And then finally, just print current's value plus whatever arrow is, and then end with an empty string. And all the while, you're telling current to equal current.next. So you're iterating through the while loop. You keep going to the next element, and then as you look at each element, you're going to make sure that you either put an arrow or no character if you're already at the end. So there's no arrow after the last item in the queue. And then finally, I want to print another line so that just to apply some spacing in the output. So that should do it as far as the list queue class. And now we can see if this works by creating a main file where we create a list queue and apply these functions. So back in the project, I'm going to right-click the folder name and click Python file and call this one main. So now this is main.py, and here's where we're going to import a list queue. And we start off right away by defining main. And so I don't forget, I'm going to put something in here at the bottom. If name equals main, then run main. All right, so now we can define the main function. I'm going to say LQ is equal to list queue. Oops, this should be import. And then just to show what happens if you have an empty queue and you try to print it, I'm going to say lq.printQ. I get what I expect. It says the queue is empty, which it should because we haven't enqueued anything. And so let's proceed. So now I'm going to say print enqueuing, if that's a word, A and B. And then let's enqueue those. lq.enqueue A, and then let's enqueue B, and then let's print the queue again. So first it says the queue is empty because we printed it before we added anything. Then we enqueued A and B, and now the queue looks like this, where the front is A and the next one is B. It appears to be working. It didn't print another arrow after B because of the condition we created on printing arrows, and that's why we did that. So it's working great. Let's add some more things and let's see what happens. So I'm going to say print and put a space in there and say dq called and lq.dq. Once lq.dq is called, it will pull that element off the list. But as a bonus, because we're returning the value of the dq'd element, it's going to tell us what that value is here in the string output. And then we're going to say lq.printq. Let's try something else here. Add a new line. Enqueuing C, let's say D, E, F, and G. So let's enqueue a bunch of nodes. So lq.enqueue, print the queue. Let's say length of queue. Let's see if that works. And get the length. And we have to convert it to a string because it's going to return an integer, a number. And in Python, it doesn't auto-convert here. If you did this in Java, it would auto-convert it for you. If you're putting it in a string, it will take the integer and make it a string, but it doesn't work that way in Python, for example. All right, so we have length of queue, and we indicate that there. And then finally, let's figure out if front works. So front of queue UE, and this is a string, so we don't need to cast it as a string. Get front, and I think that pretty much exercises all of our print functionality, and finding the front and the size, those types of things. Let's see what happens when we run this. No errors, that's good. Let's drag this up so we can see. All right, so we have the queue is empty. enqueuing A and B, so you get A to B, DQ called, and A is removed, so now the front is B. That makes sense. So then we enqueue C, D, E, F, and G, so now I have B, C, D, E, F, and G, and the length is 6. And it is, because there are 3 things there. The front of the queue is B, and the process finished. So, we were able to implement a queue in Python using a singly linked list that we modified so that we would, instead of a head only, we changed that head to be a front, and we also added a tail, which we called back, because of the unique situation that a queue entails. So this is also a lesson in flexibility. We still have a singly linked list here. We modified it a little bit for our purpose of using it for a list. So, don't think that if you have a certain type of singly linked list or a doubly linked list or something that you can only produce it in one way. There can always be variations on a data structure that maintain the essential capability of that data structure, and that's what we've done here, and in which case we've adapted a singly linked list to serve a queue. Let's go back and conclude and see where we go from here. Okay, so we were able to implement the queue, the first in, first out data structure in Python. We ended up using a singly linked list, but we modified it. Not just a reference to a head there, but a reference to a front and a back, which goes to show you can use a data structure and modify it as you need it for your purposes, for whatever you're trying to do. And in this case, we used it to implement a queue. So well done, congratulations. And in the next video, we're going to look at hash table, our next data structure. We're going to implement it using the Java, and in Python, we're going to use the built-in hash table class. And the reason is hash tables can be very difficult to implement. I will perhaps talk about some of the implementation difficulties there are there. It can be done, but it's a little more advanced than what you might implement in a beginning series like this. A hash table is essentially key value pairs. And if you think about it, that's all an array is, but each key is basically the array index. So array index 0 is 0 would be a key, and that would hold whatever value is in that array at that index. Well, if you generalize that concept to any key, not just array indexes like integer indexes, you can think about your first name being a key and then the value being your first name. So name, and then the value is, say, Tom. And then age would be another key, and then the value would be 45 or something like that, right? So I hope you've joined me in the next video for that. Thanks for watching. I'll see you next time.